And you wrote all the derivations also, which I gave you for alpha, beta, gamma. Right. So last time we saw the thermal expansion, right, of solids. Right. So in this, if you see some real-time applications of this thermal expansion of solid, right, in real on a daily basis. I'll explain this part, then we'll go to the calorimetry. See, one thing, did you ever observe on the railway track there is a gap? Have you ever observed? So the gap is actually provided for the metals to expand and contract. Okay, that is one of the applications. Similarly, for a railway track, there will be a gap in between. That's correct. One track and one track nodule or gap. Or else it will bend in this way. If there is no space, it will start bending in a parabolic format. So there is a gap that is given. Okay. Similarly, I'll just tell you which one you can understand better. Just put it to the rim of the card. So that is also made slightly smaller in diameter so that you can give it some space to expand. Actually, that is the experiment I wanted to actually show. And the apparatus coming. I'll see if it is working. I'll show it tomorrow. Okay. So next is the concept of calorimetry. So what is the principle of calorimetry? When you have an isolated system, what do you mean by an isolated system? Means if the system is not exchanging any heat with the surroundings. If you have an isolated system, the amount of heat lost by the hot object is equal to the amount of heat gained by the colder object, right? So this is what the principle states. And there are certain terms that you need to understand for the concept of calorimetry. For you to apply the formula in calorimetry, there are different ways in which heats are defined. Right. So the first definition of heat that is defined is called as specific heat capacity or specific heat. So both are same. Specific heat capacity or specific heat, both actually mean the same. So what is the meaning of it? Last class we saw a small activity based on it. What was it? So we took a balloon. When it is filled with air, you took it to the fire, it burst. Whereas when there was water, it didn't happen because water has more meaning of it. What is the meaning of it? Means you need to supply more amount of heat to make that water get heated up. Whereas air will get heated up faster. Right? So how do you define this? How do you define specific heat capacity as? So write down the definition. It is the amount of heat required. It is the amount of heat required to raise the temperature of. It is the amount of heat required to raise the temperature of unit mass of a substance. Right? To raise the temperature of unit mass of a substance through 1 degree Celsius or through 1 degree Celsius or 1 Kelvin. So the amount of heat required to raise the temperature of unit mass of the substance to 1 degree Celsius or 1 Kelvin. So how do you write it? C is equal to the amount of heat. Heat is represented by the symbol Q. The amount of heat required to raise the temperature of unit mass of a substance through unit change in temperature. The change in temperature can either be in terms of Kelvin or degree Celsius, right? So what is going to be the SI unit for it? It will be joule per kilogram into Kelvin. So which is joule kilogram inverse Kelvin inverse. So what is going to be the CJ's unit of it? CJ's unit will be calorie per gram per degree Celsius or calorie gram inverse degree Celsius inverse. So this is specific heat capacity, or it is also called as specific heat. Okay. There is another term called as heat capacity. There is another term called as heat capacity. Those who are online are able to understand. So heat capacity is also known as thermal capacity. Okay. So one thing I wanted to tell here is specific heat capacity or specific heat is either represented by a symbol C or some books represented S also. I think this you would have learned in your chemistry also. This time. Did you learn in chemistry, in thermodynamics? So heat capacity or thermal capacity. This heat capacity, what does it mean? It is the amount of heat required, right? It is the amount of heat required. The amount of heat required to raise the temperature of any mass of a substance, to raise the temperature of any mass of a substance through 1 degree Celsius or 1 Kelvin. To 1 degree Celsius or 1 Kelvin. So mathematically you write it like this. Heat capacity is equal to amount of heat required to raise the temperature of any mass of substance through 1 degree Celsius or 1 Kelvin. So Q divided by delta T is heat capacity. Q divided by M into delta T is specific heat capacity. Simple enough. Because this term is not used much. It's better to know. So the last term with respect to these kinds of heat is latent heat. So what is latent heat? Heat transfer in hidden. Okay. Latent heat na hidden heat na எழுதும் பிறகு. What changes? Temperature change does not take place. What is that liquid to gas called? So when you supply a particular amount of heat, if there is no rise in temperature, generally what does the heat do? Heat will raise the temperature of the substance. Suppose you take ice, which is at 0 degrees Celsius, and you supply heat to it. What will happen to that ice? Ice is basically in the solid form. So it starts melting. So when it starts melting, and if you try to find the temperature of that melted form of water, it will still be 0 degrees Celsius. Why is it so? Because how can that happen? The definition of heat says it should raise the temperature, but here how is it happening? So it won't increase the temperature, it is only utilized to break the bonds which are present inside. Right? So that's called as latent heat. So how do you write it? The amount of heat that is required to raise the temperature of, sorry, not raise the temperature, the amount of heat required to change the phase of unit mass of a substance from one form to another. So write it down. It is the amount of heat required to change the phase of, it is the amount of heat required to change the phase of unit mass of a substance, to change the phase of unit mass of a substance from one form to another. Change the phase of unit mass of a substance from one form to another. So how do you write it mathematically? L will be equal to Q by M. So L will be equal to Q divided by M. There is no delta T. Okay. So when it comes to latent heat, again it is subclassified into two types. What are they? It's called latent heat of and latent heat of vaporization. So LF stands for what? Latent heat of fusion. So fusion means basically liquid getting converted to solid form. Fusion means joining. Right, melting is the reverse process. So latent heat of fusion will be the same value as that of latent heat of melting, because if you want something to melt, you need to extract that amount of energy from it. Right. So what is latent heat of fusion? It is the amount of heat required to convert unit mass of ice to its liquid form. unit mass of ice to its liquid form. Then what is latent heat of vaporization? The amount of heat required to convert unit mass of barely vapor, unit mass of water to its vapor state. So those values you need not remember, they'll give it in the question. Okay. So how will you write it? Q will be equal to M into L. If I rewrite the equation, the amount of heat is equal to M into L. M is the mass of the substance, L is going to be the latent heat. Then what about heat capacity? Q will be equal to heat capacity into delta T. What about the specific heat capacity? Q will be equal to M into C into delta T, where C is going to be the specific. I just rearrange the equation. So when you rearrange it, these are the values of heat that you'll be using in solving problem based on calorimetry. Did you get a problem based on this? No. So listen, there is a sphere which is made of aluminum and its mass is 0.047 kilogram, right? So it is placed for sufficient time in a vessel containing boiling water. So obviously what will happen to it? This aluminum will get heated. Right? It is going to acquire the temperature of the boiling water so that the sphere is at 100 degrees Celsius. It is then immediately transferred using an insulating rod. They have taken it, transferred it to a calorimeter, a copper calorimeter, which contains 1/4 kilogram of water, which is present at 20 degrees Celsius. First of all, when you drop, what will you see? Be hearing some sound, right? When a hot object is dropped into cold object. So after that sound, what will happen is the aluminum rock, the aluminum sphere is actually transferring heat to whom? Heat to the water. So it is raising the temperature of water. At the same time, the temperature of aluminum is going up. Right? And they both are attaining a steady state at 23 degrees Celsius. Steady state means it is a thermal equilibrium. So what is the meaning of thermal equilibrium? When the heat of the system is balanced. Beyond that, nothing will decrease, nothing will increase. At 23, the process of something losing and something gaining is stopped. Now you need to calculate the specific heat capacity of aluminum in this scenario. Okay. So what is the story? Heat lost by dash is equal to heat gained by dash. So who's losing the heat? Aluminum. And who's gaining the heat? Water. Right. So heat lost by aluminum, it is mass of the aluminum into specific heat of aluminum into the change in temperature that is taking place is equal to, I'll write it as MAL CAL into delta T of aluminum will be equal to what is the heat gained by water? Mass of water into specific heat of water into delta T. Got it? So make a note of this one. Okay. So I need to give you the specific heat capacities. So specific heat capacity of water, write it down. They should have given in the question. So specific heat capacity of water is 4.18 into 10 power 3. 4.18 into 10 power 3 joule per kilogram per Kelvin. And specific heat of copper is equal to 0.386 into 10 power 3. Here there is something else also that needs to be added. What is it? Here something else is also having to have a rise in temperature. What will be the heat transition gap? Into a calorimeter which is made up of copper. So copper also has some mass. Heat will also slightly increase from 20 to how much? From 20 to 23. So what you should write is plus mass of copper into specific heat of copper into delta T of copper. Understood? Okay. So mass of aluminum, how much should I substitute? 0.047 into specific heat of aluminum, how much should I substitute? Into 10 power 3 into change in temperature of aluminum, how much should I substitute? For this, for copper, for aluminum, we need to find. No? That is what the question is. Into what is the change in temperature? It was initially at 100 degrees Celsius. It has fallen down to 23. So 100 minus 23 is 77 is equal to what is the mass of water? How much is it? 1/4, right? So 0.25 into what is the specific heat of copper? 386 plus specific heat of mass of copper is 0.14. Change in temperature is how much? 3. Has gone from 20 to 23. So 0.14 into specific, specific heat of water leather. Specific heat of water is 4186. And 4.186 into 10 power 3 is 4186. Right, here there is a 6. 0.14 into, this will be 386 into 3. So this is what you need to calculate. Okay. So this calculation part I'm leaving it to you. You can leave some space. So answer is 0.911. You can make a note of the value. 0.911 kilojoule per kilogram per kilo. So it is 0.911 into 10 power 3. Okay, make a note of that point alone. Here. So now the next question is the 18th one. Calculate the heat required to convert 3 kilogram of ice. Right? Calculate the heat required to convert 3 kilogram of ice at minus 12 degrees Celsius kept in calorimeter. Right? What is happening? Calculate the heat required to convert 3 kilogram of ice at minus 12 degrees Celsius kept in a calorimeter to steam at 100 degrees Celsius at atmospheric pressure. So what is there? You have ice. It is not at 0 degrees Celsius. It is at, read the question. It's minus 12. So you are given with, you are provided with the ice. So from minus 12, you need to increase the temperature of the ice to 100 degrees Celsius. So if you have to do that, then what is the amount of heat that you need to supply? That is what the question is. So here, if you see, what are all the stages that are there? First step is take the ice from minus 12 degrees Celsius to 0 degrees Celsius. Correct? Second, make the ice melt at 0 degrees Celsius. Correct? Third step. Take the water at 0 degrees Celsius to 100 degrees Celsius. And fourth step is make the water boil at 100 degrees Celsius. So these are the 4 steps for which the heat you are supplying is going to get utilized. Right? So Q will be equal to, I'll call the heat here as Q1, Q2, Q3, and Q4. So Q is equal to Q1 plus Q2 plus Q3 plus Q4. What is the value of Q1? It is M into C into delta T. See, wherever there is a temperature change taking place, write the formula in terms of specific heat and change in temperature. Right? Plus, what is the heat required to melt ice at 0 degrees Celsius? It is M into L. Plus, what is the amount of heat required to raise the temperature of water from 0 to 100 degrees Celsius? It is again MC delta T. Plus, water to boil at 100 degrees Celsius. It is going to be M into. Okay. So, write down all the values and then you can calculate. So, make a note of this. How will you go? 100 minus 12. But what about the heat that you're supplying during the phase change? Other than written heater. If you directly take it, you're only calculating the sum of the first step and the third step. What about the second step and the fourth step? You're neglecting the heat. You wrote the values. So is this concept clear? Okay. See, this is all about the second part of the chapter. I told you, right? This chapter is broken down into three parts. What are the three parts? First part is about expansion. Second part is about the calorimetry. Second part is about the calorimetry. That is heat lost by the hot substance is equal to the heat gained by the colder of the other. Okay. Then the third part is about what is it? It's about the heat transfer. Okay, we'll see what is the heat transfer all about. Okay. See, when you talk about heat transfer, see, so what do you mean by heat transfer? That is when you take an object and you subject it to heat. So what are you expecting that material to undergo? One thing is, if suppose I take a rod like this and I supply heat at this time, okay, what will happen to this rod after some time? What will happen to this rod after some time? Can I say that the heat that is supplied here will actually get transmitted to the other portions? Right? Can I say this part will also get heated after some time? Is that right? Okay. So this kind of a transfer of heat, which is taking place, what kind of a material is this? What kind of a material is this? For a solid, it's called as, what is this kind of heat transfer called as? So you call this as conduction, right? Similarly, what is the other type of heat transfer you can think of? The other is called as convection. So where does convection take place? So in conduction takes place in the case of solids. And what is the third type of? So radiation. So radiation does not require any medium for propagation. So for conduction, you need a medium. What kind of a media do you need? Or medium do you need? You need a solid medium. For convection to take place, you need a liquid or a gaseous medium, right? And for radiation to take place, you don't need a medium at all. The best example, you can think of electromagnetic radiation, which our mobile phones are using, right? See, this chapter and next chapter is right. I can do nothing. I'll try my best to show it through activity. 13th is worst. First chapter on the planet. I'll be gaseous state with chemistry. Very chapter. Because it's good for mechanical engineers, but classic 14th and 15th is excellent chapters. Waves and mechanics, simple harmonic motion. Because I can show something practical. I'll try my best. This one is very good, especially rotation mechanics. It is very good chapter. If you are able to master that 75%, 75% சொல்ல மாட்டேன் 50% physics and but you will apply it in many other branches also. Okay, I'll just give you a brief outline of what is conduction and radiation is. So what is this conduction all about? If there is a transfer of heat taking place, See, transfer, what should happen? It should travel from one point to another. That is the meaning of transfer. So if there is a transfer of heat taking place in a substance, especially solids, from one end to another end, without, okay, make a note of this point, without the actual movement of particles. Without the actual movement of particles, then you call that as conduction. I repeat it. If transfer of heat takes place from one end to another through a solid without the actual motion of or movement of particles. Actually, cancel that word motion. Without the actual movement of particles. M-O-V-E-M-E-N-T, movement of particles from their mean position. Is called conduction. Okay. So first write down the basic definition, then I'll get into the mathematical details. First, you have to visualize it up down. Okay, next is convection. What is convection? Heat transfer that takes place in liquids and gases with the actual movement of particles. Heat transfer that takes place in solids and liquids, in liquids and gases with the actual movement of particles. Then what is radiation? What is radiation? Transfer of heat. Are you guys waiting for radiation? Convection. Okay. So radiation means what? Transfer of heat from one place to another without an intervening medium. So there is no medium that is required, right? So radiation means what? Transfer of heat from one place to another without an intervening medium. And intervening medium. Okay. So one minute. Now we'll do some activity. The activity tomorrow I'll explain about the mathematical parts of it. Just give me a minute. Just clearing the data. Solve more. அதுதான் சொன்னேன், பார்த்தா தான் தெரியும், அதுக்காக wait for 10 minutes to get the answer. You're only going to do, I'm not going to do. You're going to play with fire. Just clearing the data. என்னம்மா? எது? பண்ணி பாரு. எக்ஸ்பீரியன்ஸ் எப்ப வீட்டில் பண்ணியா? இப்ப திருப்பி பண்ண எக்ஸ்பிளைன். இந்த டேப் யூஸ் பண்றாங்க. The fan will be off. Don't sweat. Don't sweat. Sorry. So then also see. It is better அங்கே இருங்க for them to block. Okay. Sounds really good. waves is over in your school? Gravitation. First one you know.
Second one.
Oh, rotation mechanics are there.
As you know,
So will be the time is very slow. Feeling very guilty that I am slow. I saw rotation mechanics. Even okay, fast slow. I cannot accept my defeat. Not very fast or very slow, but okay, medium speed. It's okay, I don't want to. School pressures are found here. They have to complete the syllabus. Okay. Those who are online are able to see them. If you are live on this,
Yes, sir.
I will be from. Yeah, who's coming? Okay. Already straight away. Actually, in the book. You guys will complete. Who's coming to do this? The fireman, very happy. Yeah, that's one. Right. Who's going to do? So then, so hold it here, right? So you're able to see this ball, right? Confident of it, cooking in the so either this ball, and you have a rim here. Are you able to see this? Camera. So you're able to see a rim, right? And this ball has a specific diameter, due to which, when you pass it through this rim, see what is going to happen. Show it to them also. Like put it from the top, up here. You put it. Release one. Release one. So what is happening? So the diameter is kept slightly lesser than the diameter of the ring. Diameter of whom? Diameter of the sphere is kept slightly less than the diameter of the ring. So it is made up of metal. Right? Or metal, you are able to sense the weight, right? So you keep it here and heat it for some time. According to chemistry, there are layers of fire. Which layer will be hottest? Layer. That is the hottest. Right. So you're able to see this fumes coming. Okay, I don't want you to touch. Show it to me. Now, it's very hot. Okay. Okay, same. So I've taken this. Okay, I'm trying to put it through this. Observe what is. You heated it when it is on the other side. So it is actually going, means we need to heat it for some more time. Right? Let us heat it for some more time. So what is expected out of this? So what should happen according to the theory? Go inside. If it goes inside, then physics fails. right? So I need to heat it, no other option. I need to have some patience. So through this, you can understand another concept also. That is just the concept that we discussed now. What was it? Conduction, right? So I am heating the material here, but I'll not be able to touch it here also. Okay, just keep your hand empty, don't keep it for longer duration. Are you able to sense some heat? So why is it happening? Because there is conduction. If you see, there is actually no movement of particles. The sphere is here only. The ring, the parts of the chain are still intact. But what is happening? The heat alone is getting transferred. That is why when we define conduction, what did I tell you? That there is a transfer of heat taking place without the actual movement of particles, right? I need to heat it for some more time. When this heat is not sufficient, okay, I need to have a bigger heat. But you are able to understand the concept, right? So what we are doing is, there are two things. One is conduction, and the second is thermal expansion of solids as well. So if you want, you can replace this with another ball also. So this is about the expansion. You're able to see the soup that is getting formed, right? So in the soup, Pati will do something else also, right? Now, the question is, what I think last week I did it, but I'll do it again. This is made up of, what is this candle made up of? It is made up of paraffin wax, right? So paraffin wax is again a chemical substance, right? Now it is ready to get burnt. You are able to see some liquid wax getting generated and everything. Now, when I switch it off, I keep it here, the heat is actually traveling. How is it? You want to try and see? Blow it off. How is it happening? So what exactly is this thing? Last week I explained. What exactly is happening here? It is a wax. So it looks like smoke, right? Actually, it is not smoke. It is vaporized wax. So that is why even in the air, it is ready for the combustion process to take place. So whenever you have wax supplied with enough amount of oxygen, then it is ready for combustion reaction. Okay, so that is why the heat actually got transferred, right? So now what are the concepts that we saw? One is conduction, the second is convection. You want to fire அதை பார்க்க கூடாது ஏன் அதே பார்த்து இது என்னதுடா what is this
It's a chocolate company.
some wrap அதுமா
Water paper.
basically the tea wrap இருக்கு the tea powder was emptied and this is taken okay இப்போ இப்படி எப்படி வச்சிருக்கேன் புரியுதா என்ன பண்ணலாம் இதுல இருந்து take some fire and heat it கொஞ்சம் பின்னாடி வந்து leave it, right? So it's nicely getting burned, right? Now see what will happen suddenly. What happened? It went up. Why?
So due to heat, it became light.
So what kind of heat transfer is this? This is the example for convection. That is the actual movement of particles. Are you able to visualize what I am trying to say? So conduction happens without the actual movement of particles, whereas for convection, it actually travels. So when it became light, right, what happened? It started, when it became light, no, due to buoyant force, it started racing upwards. So when it started racing upwards, it went to a certain point and it was completely emptied and fell down, right? So this is an example for convection. Okay, radiation you're using in a daily life. Right? Radiation is the electromagnetic radiation that we speak about, mobile phones and everything, right? So this is there. Okay. Now, I don't know if it will work, but let's try it. Who's going to do this? Who wants to do this? Shri, all right. Okay. So what I want you to do is, now I'm giving you a task. Okay. You've joined a company. Company learn R&D head. Okay. And they're expecting you to design a machine where you use physics to lift this bottle without actual usage of hands. So how will you do it? I don't want you to use it. So I want you to use physics so that you're able to lift this bottle. So as R&D head, what will you do? Balloon வச்சு ஃபயர் பண்ணுவியா? எங்கே ஃபயர் பண்ணு? கீழே இருந்தா எப்படியா? இப்படி வச்சு என்ன பண்ணுவீங்க? எங்க ஃபயர் பண்ணுவ? வேர் வில் யூ ஃபயர் இட்? இங்கே தான். இது வெடிச்சிருக்கேன். That's what happened last time. When I took it to the fire, it burst. உள்ள கேண்டில் வச்சுட்டு மேல வைக்கணுமா? It's the same thing again. No, still fire. It is still going to be hot now. I'll clear that out. She's saying put a candle inside and keep it here. Still the heat is being supplied because it has oxygen supply now. Unless you are going to cut the oxygen supply, how will you make this exist? There's actually a small part. Let's see what happens. Okay. So what did you say?
Sir, hot actually continue.
So how will you fill that hot air? So you want to say, so initially you have air inside. So what are you going to do? You're going to fill in some hot air. How will you fill the hot air? So how will you heat it? I've given you all the equipment. You can do. I've given you everything. What will you do? Right now, you already told the answer. You're right. You told the answer. Expand it. So expanding means inside you need heat. Where do you take the heat from? You cannot take the candle and directly put it inside. So I've given you a material which can actually heat. Okay, take it and put it. It's working. Right. Our R&D is a success, right? So what actually happened? When it was burning itself, had I put this inside, it would have burst because of the specific heat constant. But what did I do? When the air got expanded, the air particles were actually trying to rush out. This was actually blocking it. So what happened? The pressure got developed in such a way that the value of pressure inside got decreased because the volume went more, pressure decreased. So the pressure decreased, the outside pressure became more and it started moving in naturally. See? I'm able to hold it without the actual usage of magnet. Right? It works. Right? So this is how your thermodynamics actually works. Right? Let us expand it. Maybe we can keep it as a good question. Try till the outside pressure is more than the inside pressure. When it is there, then what will happen? It is at equilibrium now. Right? Now we are able to lift it and see. Works. Right?
So direct on the glass.
Direct on the glass. Show you more. The camera. Okay. See. See, if I directly heat this glass, Candle. I wanted something else to. Tissue paper. So you're able to see a suit being formed, that black color thing. It takes a lot of time. So you're able to see this. Okay, the water. Okay. So you're able to see this water drop. See what happens to this water drop. Actually moving like this, right? This is what is called as absorption. Absorption. You're able to better move over. So you're able to see. Especially on the suit, right? Actually, it will form a liquid drop itself. We need to do it more precisely. Maybe I'll try it again in the exact sphere. Maybe. So it looks like an exact sphere. See. It looks like an exact sphere. Whereas outside, so this forms it because the suit is actually forming a layer from the water getting stuck to the glass. Other points they are able to see the water getting stuck to the glass, whereas here it is not getting stuck. Look at the water drop that is moving actually. It is acting as a layer, which is separating from which is actually decreasing the adhesive force. Okay, so this is what happens. For those who are online, right? I don't know how to show, but konja bend pannu. Guys, are you able to see this water drop?
Sir.
Yes, sir.
See, water drop is actually moving. Right, that water drop, sorry, it fell down. Yeah, it took a perfect spherical shape and it was moving, right? So it is because it is actually decreasing the adhesive force. And the cohesive force is actually more. So that is the reason why this kind of a phenomenon took place. See, with the itself, we can do so many things. Right. The next one is, see, I have some water drops here. Okay, I put this into water. Obviously, it won't, right? Whereas, if I take some wax here, right? I took some layer of wax. Now I'm dipping it in water, right? I can take proper. So when the layer of wax was there, it actually supported the combustion. Whereas if it was not there, when water was there, it was trying to stop because it was trying to cut down the oxygen supply.
How is that?
It's forming a layer. So the water is actually not disturbed. So when that part gets lit up, it does nothing. So because the wax is already readily combustible, right? When the vaporized wax also went up, it was ready for combustion to take place. Right? Say then you wanted to try and see. But do it carefully. Hold it like this. Right? Hold it against the gravity. Yes, புரியுதா? நான் சொன்ன மாதிரி இப்படி வச்சு keep அவ்வளவு ஃபாஸ்டா சுத்தக்கூடாது, அகர்பத்தி சுத்துற மாதிரி. ஓகே, இல்ல ஸ்லோவா பண்ணும். You're able to hold it, nothing is happening. No. சுத்திட்டியா? So you're holding it, now you can't hold. So comparatively, I could hold it for a longer duration. Even I had that. Okay, I could hold it for a longer duration because right. So this is what happens. I do so many experiments with heat itself. புரியுதா? Because when you're holding it like this, water. When you're holding it like this, it is actually heating up the surrounding air particles, and these air particles are raising due to convection. So they were heating your hand. But when you keep rotating it, you're not giving enough time for the same layer to get heated. You're changing the direction. It's like friction. So when you're changing the different layers, what is happening? They don't get enough time to get heated up to the extent that is happening when you keep it stationary. So that's why it is. Hold like this, nothing is going to happen. Oxygen is coming from the bottom. It is not going to hit your hand. So when you hold it like this, what is happening? The air particles are obviously raising up. Your hand is actually acting as a blockage for it. That nothing will happen. Nothing should happen, right? So logically, nothing should happen because these air particles are obviously due to density, they are raising upwards, right? So I'm able to hold it. Whereas when I hold it down, you are actually blocking those air particles. So obviously, what will they try to do? They'll burn your hand, right? When you hold it like this, nothing. So it is going upwards. So that clearly shows how buoyancy works. Are you able to visualize what exactly is buoyancy also? Right. So this is how convection works. Right. These are all the small activities which I wanted to show you. Hope you could understand something. Right. Why you are studying this. Right. Or at least you would have understood what are the concepts, right? Anything else?
Bowl candle வச்சு க்ளோஸ் பண்றேன்.
அதுவும் அதேதான், same concept, volume expand. We'll do something else tomorrow. I'll show you how the thermodynamics. Okay. So I hope you could understand, right? So now you know what is conduction. Yeah, what is it actually? With understanding, I must. So what happens in conduction? Actual heat is getting transferred from one point to another without the actual movement of particles itself. What about convection? You saw with the tea bag, right? So what happens in the tea bag? So heat transfer along with the actual movement of particle. The particle itself got raised. So that is an example of convection. Radiation we already discussed. Then what are the other concepts? When you hold it like this, what is happening? Can you give me the explanation for it? Due to buoyancy, the air particles are trying to raise. What air particles? They are hot air particles that are actually trying to raise. Due to whom? Due to the decrease in density, because the volume is increasing. So due to the decrease in density, when they are going to raise up, since you are blocking it, your hand is burned. Whereas when you keep it like this, the air particles are escaping where your hand has nothing to do. Similarly, if you keep it in the reverse direction, also nothing is going to happen. Similarly,
Flames upwards because of buoyancy.
because it is heating the air particles surrounding.
No, sir, it is always pointing upwards, right, not down.
Because the buoyancy can be opposite. With the flame, solriya. See, flame, it is because of the oxygen only. I can't say, I don't know exactly if it is buoyancy that is coming in picture, but I can say about the air particles which are surrounding when you switch it off. You saw the particles going upright, unless you are going to give a forced convection. So when you talk about convection, again, there are two types. One is called as natural, the second is called as forced. Natural convection is something which is happening like that. It is due to the natural parameters. Forced convection is something like where your refrigerator or air conditioners work. They work on the principle of forced convection. Because what are you trying to do? You're actually trying to do something in the reverse process. You're actually trying to cool the substance by making it lose energy. So it is a reverse process which is possible only through forced convection. Purida. So this is the outline.
சரி, இப்ப நம்ம கேண்டில் வச்சு கேண்டில் தலையில
Fire will come up. And wax will fall down. I'm saying I'm able to sense heat. The bulb.
So you can kill, sir.
Look at the way wax is falling. It's creating a soot here and it's falling. But the wax is getting burnt at a faster rate. I'm able to sense. When it is hitting my hand, I'm able to sense it. Clear? This one, we tried. Nothing has happened. A smell or the rubber. The reaction and looking good. Rubber the formula when it's heated.
It's a burst.
Which is suit American. Because big it would have heard I'm waiting for getting a sound there last later. The ball and right? So more air, the pressure was more. Time in
That's 7.
7. Another class of right. So tomorrow we'll see the mathematical expressions for conduction, convection, and radiation. Once that is over, we'll see the thermodynamic. Kinetic theory, I'm not going to teach. If you don't ask me to teach the chapter, I get bored. There is nothing to teach. So kinetic theory alone, go through the recording, and it's an important chapter for the career. From the 12th standard perspective, but simple harmonic motion and waves are very, very important and teach in detail. That's what a practical as well. Musical instruments will just be. To enjoy it. Okay. Then the chain is blocked. And I put it in down. Okay. Okay.
Thank you, sir.
Guys, those who are online, you can leave down. You're done. Okay.
Thank you, sir.
Yeah.
Thank you.